All of the advantages of the Laplace transform come from its mathematical properties, so it seems reasonable to take a glance at them. There are a bunch of properties, but we will only mention those that we'll be actually using during the course, and in particular 6 of them. Each one of these properties arises from a different theorem, but here we won't give any proof for those theorems. The interested listener can always check them out in any math book. So let's go with the first property, whose name is linearity. The Laplace transform is a linear operation. This actually involves two separate conditions. The first one is called additivity. Also, this is called the superposition principle. And this principle states that if we have two separate functions of time, or two functions of t, for us these are signals, functions of time, f of t and g of t, the Laplace transform of the sum of those functions of f of t plus g of t is the sum of the Laplace transform of each one of them. That is, the Laplace transform of f of t plus the Laplace transform of g of t, or in other words, capital F of s plus capital G of s. The second condition contained in the linearity property is called homogeneity, also called the scaling property, and it says that if we have the function f of t and also a constant k, the Laplace transform of k times f of t, the multiplication of the constant by the function, is equal to the constant times the Laplace transform of the function f of t, or in other words, k times capital F of s. Sometimes these two principles, the superposition principle and the scaling property, are expressed together in a single equation, like this one: the Laplace transform of a constant a times a function f of t plus a constant b times function g of t is equal to a times f of s plus b times g of s. Alright, we can go on to the next property, which is the real differentiation. Real differentiation. And this property tells us that if f of t is differentiable and its derivative f prime of t it's transformable, then the Laplace transform of the derivative of f with respect to time, the derivative of f of t with respect to the t variable is equal to s times capital F of s minus f at 0. That is, the Laplace transform of the derivative is equal to the variable s times the Laplace transform of f minus the value of the function f evaluated at t equal to 0. As we can see, a complex operation like differentiation has been replaced by a simple one, which is a simple multiplication. Now we can go on and tackle the second derivative of f of t by applying the same principle. The Laplace transform of the second derivative of f of t with respect to t twice, and here we're going to use a little trick. We'll rewrite that in this way. This is the derivative with respect to time of the derivative of f of t with respect to t, and we'll call this derivative the function g of t. By the way, here we've assumed that f is twice differentiable and that its second derivative is also transformable. So here we're having exactly that with g instead of f. So we get s times g, capital G of s minus g evaluated at 0. Now let's replace g of s by its meaning. Here is we have s times the Laplace transform of g of t, which is the derivative of f of t with respect to time, and the minus g of 0 is equal to minus the derivative of f of t with respect to time evaluated at t equal to 0. That is, s times, I open a bracket, and here we have to write this, which is s times capital F of s minus f of 0, and this part here is simply f prime evaluated at 0. So here we have minus f prime of 0. So finally, the Laplace transform of the second derivative of f of t is equal to s squared times the Laplace transform of t minus s times the function evaluated at 0 minus the derivative of the function, the first derivative, evaluated at 0. So if we continue with this process until the nth derivative, we get a general expression. The Laplace transform of the nth derivative of f of t with respect to t n times is equal to s to the n power, to the number of differentiations that we are assuming, times the Laplace transform of the function, minus s to the n minus 1 power times the function at 0, minus s to the n minus 2 times the derivative of the function at 0, minus all the way until the n minus 1 derivative evaluated at 0. Now, notice how the Laplace transform includes the information related to the initial conditions in the problem since the very beginning. This will be very helpful when solving initial value problems, that is, problems given by differential equations and the initial conditions of the functions. We'll learn about that in future videos. We'll benefit from this nice property. But first we need to go on with other properties, and here is the third one: real integration, actually the kind of counterpart of the previous one. Real integration. So if f of t again has a Laplace transform, the Laplace transform of the integral from 0 to t of f of tau d tau is equal to, most of you have probably guessed that this has to be f of s instead of multiplied divided by s. So in integration, instead of multiplication we get division, but it's the same principle. This can be generalized as well. So the Laplace transform of the compound integral from 0 to t1 of the integral from 0 to t2 all the way to the integral from 0 to tn of f of t tau 1, the tau 1, the tau 2, the tau n is the Laplace transform of the function over s to the nth power. In the next video we'll present another 3 nice and useful properties of the Laplace transform.